We're pleased today to welcome Stephen Griffies from NOAA's Geophysical Fluid Dynamics Laboratory at Princeton. In Princeton, and at Princeton too, right? You also have an appointment at Princeton.
Yes.
Right.
Yeah.
So Steve Griffies got his original degree as bachelor's in chemical engineering back in the 80s at Louisiana State, and then a master's in engineering at Northwestern University, and then finally a PhD in theoretical physics from the University of Pennsylvania. And started out in what appears to be quantum gravity, publishing papers with titles like non-perturbative stability of supergravity and superstring vacuum. But eventually decided not to go into quantum gravity and instead went into global climate and ocean modeling, and was a UCAR
Climate and Global Change.
Climate and Global Change fellow at Princeton University starting in 1993, and then has been at GFDL basically ever since. Since 2000, he has been the co-leader of the Ocean and Climate Model Development team, and since 2001, the leader of the GFDL Oceans and Climate Group. He has won numerous awards for outstanding papers, and recently won the EGS Manson Medal for oceanographic research. He has done a lot of work on ocean modeling, not surprisingly, and sea level rise, and climate change, and heat flux. And he's going to be talking to us today about heat flux due to mesoscale eddies. I understand you've only been to sea once, right?
Yes.
Which was in the Labrador Sea, and that was probably enough to...
I have dreams of going back again to the Southern Ocean next in about 18 months. I've signed up.
Ah, dang. I've only been to sea once too, and that wasn't enough to...
I figure I don't want to die before I go to the Southern Ocean, but I don't want to die going to the Southern Ocean. Don't you? Thanks for coming, and thanks for having me. I really have enjoyed my time here so far, and I'm going to talk a bit about some of the modeling that we've done in the last few years at GFDL, looking at the influence of the ocean mesoscale eddies on the transport of heat in the climate system. And some of this work builds on pieces of work that Christopher Wolf and others have done. And so there is some novelty, of course, but there is, of course, as any science problem, you're resting on the shoulder of those that came before you. So let's see if I can do this right. So we're going to be looking at some motivational questions for this talk to explore the ocean mesoscale from a climate perspective. I'm not going to be showing you detailed information about the dynamics of the eddies themselves, as sort of somebody, an ocean storm track kind of person might do, but I'm going to look at their impact on questions such as the mean climate state, the climate drift, and some transient climate sensitivity. In fact, I'm not going to talk about this third one, but it's something that has been done subsequent to this piece of work, mostly looking at the first two bullets here. Are questions from mesoscale eddy absent models readily transferred to mesoscale eddy active models and rich models? Those are questions that the climate community continues to ask. We're constantly constrained by computer power, but I think that the universe has been kind in that we have not gotten the most powerful computer to solve, at the Kolmogorov scale global climate. We have been forced to think about things as the scales are resolved, decade by decade of our time. Each little bit of scale, you get more and more resolved in the simulations, and you have more time to think about what you're getting. And that's kind of at the mode we're at now with these climate models run for multi-centuries with the ocean mesoscale represented in a way that has not been done before. And this is an example of that exploration that we're in the process of doing, which will probably take about 20 years before we know what we're doing. So I'm going to describe these three models that we've built at GFDL. It's a hierarchy of models that we call in CM2O, O for the ocean. and look in particular at vertical heat transport from the transient eddies. And a piece that I'm not probably going to have time to talk about is looking at poleward heat transport from the mean currents, in particular the subtropical gyres. And give you some perspectives. So the bulk of this work came out earlier this year in a Journal of Climate paper, which has the typical multi-authored team of people that are necessary for building these kind of models. And let's get into it. What is the ocean mesoscale? Well, as we define it in the ocean, it's really the size that is determined by the first baroclinic Rossby radius. Mesoscale features are the whirls and eddies, the storms of the ocean. And of course, even on top of those scales, the cutting edge is looking at the submesoscale, the scales that are even smaller than the mesoscale. But this model does not get down to the submesoscale. It gets down at best to the mesoscale. And the scale that is really relevant for that is the Rossby radius, which is some phase speed over the modulus of the Coriolis parameter. And you can write the Coriolis, the phase speed as the vertical integral of the buoyancy frequency. So global models are marginal at representing this scale. Regional and process models are just reaching the mesoscale. So why is this scale so important? Well, these whirls and these eddies, this is a slice off Tasmania here. Beautiful picture of some eddies off the east coast of Tasmania. These eddies have a lot of impact on the transport of properties in the ocean. Momentum, tracer, heat, carbon, other processes, biology. So we don't represent these eddies very well in models, and so you either have to represent them with a very expensive model like I'm going to show you today, one of, or you have to parameterize them. The parameterization of these features has been a 20 to 30 year problem in theoretical oceanography that continues to pose interesting questions that push the community forward. But we're now getting to the point where we can afford to represent these eddies explicitly, and let's see what they do, is kind of the question that I'm going to ask today.
What's actually being shown in that?
It is an aqua modus false color, I think, ocean chlorophyll. It's a beautiful picture, though. I think it's one of my favorite from Modus. Modus, if you go to their website, you can see lots of images that you can download and show in nice talks like this. So the resolution required for representing these mesoscale features, it's not really well defined what you mean by resolving. But one of the ways of defining or posing a definition that is at least you can discuss it is according to the Rossby radius of deformation. The first baroclinic Rossby radius of deformation, I gave you a definition of that on the previous slide. And this is a figure from a colleague of mine who shows, Bob Hallberg, who shows an image of take the ocean stratification and the bottom topography and calculate that first baroclinic Rossby radius and say you need 2 grid points to represent that scale. What is the resolution required? And as you can see, as you go to the higher latitudes, you need finer resolution. And as you go into the shallow ocean, you need even finer resolution. So in the mid-latitudes here, in the lower latitudes, you need roughly a 1/4 degree, maybe 25 kilometers or so. As you go to the higher latitudes, a 1/10 degree will represent sort of the scales roughly down to 50 south, barring the shelf regions, which require very fine scales. And as you go to the middle of the Southern Ocean, you need very fine scales down to around a 1/16 of a degree or even down to a couple of kilometers to get the resolution along the shelves. So when you hear the word eddy resolving climate model, that eddy resolving is, number one, not well defined, but number two, is subject to what you mean by resolving eddies where. Okay, so the eddies are scale dependent. They depend on the stratification and they depend on the Coriolis frequency. So they are very non-homogeneous. The ocean turbulence, the ocean field itself, the currents of the ocean are very non-homogeneous. So what I'm going to show you is a 1/10 degree, the highest resolution in the models that I'm looking at sort of get up to this yellow region, which starts to be marginal resolving of eddies in the higher So just to give you some context, working at a climate sort of lab at GFDL, there are lots of competing processes that we want to represent in our climate models. It's actually an old schematic, but it nonetheless serves its purpose in identifying the many, many different features that are required to represent Earth system models today and are being thrown into these models to help us understand sensitivity of the climate and understand what will be happening and what is happening with the change of climate. So the ocean sits over here. It's one subset of a huge process, a huge class of processes needed in these models. So it's difficult for somebody like myself at a climate lab to say, let's put all of our energy into resolving the mesoscale ocean fields, because you're going to have smart people in the atmosphere saying, no, 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 you need to have dynamical cores that have much finer resolution to resolve the hurricanes or the tropical cyclones. And then you say, no, I need to have 100 aerosols in my atmosphere and 100 tracers. And no, I need to have 5 different soil types that go down to 50 meters into the soil layer. So it's an iterative process that you sit down with a lot of different people with a lot of different perspectives, and you try to work out what is conceivable and what is doable with the resources you have. And then you move forward to try to understand the science that you can address with those resources. This is a time series of the resolution as given up to roughly 2010 of our ocean models. And it's around here at about marginally cutting at the 10-kilometer range. And so if you want to gauge your career in oceanography and computational oceanography based on this extrapolation, you might see, oh, well, where are we going to get to at my retirement? Submesoscale resolving global models, Langmuir resolving models might be the end of this century. So that is a sort of context to give you that, even beyond Langmuir resolving, we're not getting anywhere near the microscale, for example. So it's going to take us a long time before the question of subgrid scales is obsolete, if ever. The other thing that's important about understanding the processes of the smaller scales is that to parameterize them also requires understanding them. So they sort of come together as a package. So it's an interesting perspective on the evolution. Clearly, there'll be one-off experiments that push that resolution. There's one-off experiments now that are getting down to like 1 kilometer global or 2 kilometer global, but they're run for like a decade or so. They're not looking at climate yet. So our simulations, which represent this fine-scale stuff better for climate, well, that's really a question that is still being addressed. Utility for climate implies trust, which requires experience, evaluation, and experimentation. You can't just expect to run one simulation and expect to get a simulation that has high integrity. You can get some one-off experience with doing that, but to do climate, especially at a lab like GFDL, you really need heaps of experiments and lots of ensemble members to really to understand what you're getting. Presently, there's relatively little experience with eddy-rich climate simulations. Often, they're very expensive to do routine hypothesis-driven experimentation. The eddies give you more kinetic energy, but they also may mess up your water masses if the biases are large, for example. So the longer you run these simulations, the longer you have opportunity for the biases, which could be large or small, to accumulate over time. So do models of many eddies need fewer parameterizations? Well, in principle, yes, because you're representing scales that you formerly were having to parameterize. But in practice, the simulations are still, we find, sensitive to the subgrid scale. There's no free lunch in this game, in the sense that you can just resolve stuff and the boundary currents all separate at the perfect point and your eddy energetics is perfect. There is still a lot of thought that goes into both the numerics and the physics of these high-resolution models. And the question is, why are the simulations still sensitive to the subgrid scale? Is it because of inadequate numerics? Is it because of inadequate parameterizations? Is it because of inadequate representation of the boundary interactions? I think it's all of the above. We are still trying to wrap our heads around a lot of the issues related to better numerical transport schemes, better parameterizations. How does the ocean dissipate, in particular? How does it dissipate its energy? And also representation of boundaries. Boundaries in the ocean are key. One of the biggest advances that you get when you resolve stuff better is a resolution of the boundary. of the ocean. It's a non-trivial fractal sort of structure that has a lot of processes that are key that happen at the very fine scale. And again, we're far from a DNS of global ocean climates. So we need numerics and physics that's intelligent. We need some of these sort of jargon terms, monotonic and higher order advection schemes, robust vertical coordinates, and thoughtful multi-scale subgrid scale methods that are scale aware. So after that sort of intro and my philosophy on what we need to be focused on building these big models, let's look at this climate model suite that we built using some technology which is kind of state-of-the-art almost 10 years ago, but still that's about the time scale that it takes to start. You have a state-of-the-art numerical methods, then you start to configure those codes into these big models. It takes a while. So there was a paper that a colleague of mine, Delworth et al., wrote in 2012, which outlined these models. So from an atmospheric perspective, all the atmospheres are the same in these climate models, these three models that I'm going to talk about. 50-kilometer atmosphere with a land model on the same grid. And that's a pretty fine resolution. The earlier climate models of GFDL had about a 200-kilometer atmosphere or 250-kilometer atmosphere. So going to 50 kilometers, in some idealized simulations, you start to represent tropical cyclones, category 1 or 2, in some of the simulations. So it's a respectable simulation representation in the atmosphere. The ocean that I'm focusing on is based on the MOM5 code. There's a 1 degree, a quarter degree, and a 10th degree representation of the ocean with 50 vertical levels and this bipolar Arctic cap. And here are the vertical levels. The Arctic, the singularity in the Arctic is split, and the spherical singularity is split and put over land, so you don't have this problem with a coordinate singularity inside your domain. That's something that's fairly standard in the ocean community today. So here's a sort of picture that gives you a sense for what you represent better with a 1 degree versus a 10th degree. And here's sort of dolly vision of Lincoln, and this is a photograph of Lincoln. It's sort of just to give you a context for what you're starting to see when you're representing this the ocean at a scale that's finer. Now this, if you're looking at Long Island or whatever, this would be coarse. Okay, this is like 10 kilometers roughly, whereas you need to get down to 50 meters or so, or even finer when you're looking at estuaries. But for global climate, this is pretty fine scale. I like to show this picture because when I was transitioning from physics into climate modeling at the University of Pennsylvania, there was a geologist there who tried to convince me, don't do it, don't do it. They're just doing dolly vision of the planet. And I go, well, there's some physics behind it too, and maybe by the time my career gets a little more mature, it'll be higher resolution. And so this picture I love of Lincoln, you can really only see the system once you scan out, further out. And this is really the class of models that is common today in what's called CMIP 5. So the numerical formulation, this is for the people, the experts in the room. Ocean is a hydrostatic Boussinesq primitive equation. We have a fairly unique, or a nice tracer advection scheme. We have a vertical coordinate called Z star, a fairly nice representation of bottom partial steps, no slip sidewalls. We have a diurnal cycle. Here are the time steps for the model. It's as I said, it's state-of-the-art numerics and sort of physics of 10 years ago, but put at a very high resolution. So in regards to the common features amongst the ocean, the lateral processes have similar friction operator. The vertical processes have very similar vertical processes. The 1 degree ocean has a parameterization of the mesoscale, which is kind of generic. It goes under the term Jensen-McWilliams. It's a very famous paper, now 25 years old, with our flavor of that Jensen-McWilliams scheme put into it. Whereas the quarter degree and the 10th degree have no parameterization of the mesoscale field in the trace equation. So really the comparison is much cleaner between the quarter and the 10th degree simulations, whereas the 1 degree is kind of sitting there representing what you can do when you have a parameterization into the of the mesoscale at that resolution. So I'm going to look at what we call present day simulations, which is using 1990 radiative forcing. So the CO2 in the atmosphere is fixed at 1990 concentrations. The ocean temperature and salinity initialized from a year, running an ocean forced simulation using a protocol known as CORE for Coordinated Ocean Ice Reference Experiments. We ran for 140 years as a couple model, which may not sound like a long time from a climate perspective, but it's about as much as you can get from these models with the computational resources. And it's long enough to look at some of the initial decadal to centennial drift in these simulations. And my interest is in the transient. I'm not trying to get to the time mean, order 1,000, 2,000 year steady state. I'm interested in how these models drift away from initial conditions and what are the processes creating that drift. And I'm going to look at eddy mean flow decomposition to look at the heat. In particular, how does heat move through the ocean in these three different simulations? So here's a snapshot of, or a daily mean surface speed from the suite of simulations. 1 degree, quarter degree, and 10th degree with a log 10 base to sort of highlight certain features. So you can start to see the 1 degree has this sort of blurry, dolly vision perspective on the ocean, whereas in the quarter degree and the 10th degree you're starting to see some more features. In particular, you see the Gulas rings in the quarter degree and the 10th degree. You start to see these boundary currents and the features in the North Atlantic, and the Kuroshio region and the Southern Ocean starts to have a more jet-like structure, whereas it's really blurry in this simulation. And you even start to see some of the coastal currents around the Antarctic coastal current around Antarctica. So one of the ways we use to evaluate the integrity of these simulations is based on comparison of the variability of the sea surface height as compared to satellite. We have 20 years of satellite measurements now looking at sea level, and we can look at variability, temporal variability of the satellite down here as analyzed under the acronym known as AVISO, which is basically an analysis of that satellite product. And with the AVISO product, you see lots of variance in the boundary currents, the Kuroshio, the Gulf Stream, the Agulhas regions around South Africa, the Zapiola region around South America, and the Southern Ocean, the Antarctic Circumpolar Current, and the East Australian Current. The 1 degree, you don't see much at all. You see some stuff happening in the higher latitudes, which is missing. The AVISO stops at around 60 north. And those features are present in all three models, and they're interesting. They're barotropic waves circulating around the shelves of the Arctic Ocean. They're very fast. But when you start to go to a quarter degree and a 10th degree, you start to see some of these boundary current features popping out in the simulation, as well as around the Southern Ocean. One of the things that is very good in this simulations, in both the quarter degree and the 10th degree, is the Kuroshio region. It seems to be quite well represented, but the Gulf Stream, there's still problems with the Gulf Stream, even in the 10th degree. And we think that problem in the Gulf Stream is related to problems with overflow representations in the higher North Atlantic, especially in the Labrador Sea and the Gen Seas. We're not doing too well with the representation of deep water formation in the higher latitudes, which has some impact on the Gulf Stream itself. Nonetheless, there is a lot more eddy activity. And in particular, in the 10th degree, you start to see a lot more activity in the Southern Ocean. In fact, when you do a zonal mean of that, you see some places where the 10th degree gets more eddy variability than the AVISO product itself. Part of that could be the AVISO product is a limited data set. It's sampled only so much, and could be that the ocean model is in fact too energetic. I kind of doubt that, though. So this is one way that you use observational products to evaluate the integrity of the simulation. So from this perspective, from a sort of climate perspective, the energetics of the 10th degree ocean are substantially greater than, of course, the 1 degree, and even more than the quarter degree. So we're thinking that the 10th degree is a better representation of the real system. So that's the underlying assumption. And I think it bears out in some of these evaluations. So I'd like to show you a pretty movie. When you have these models, you're sort of obliged to show movies. So here's a movie of New York City, which I went through on a train. And you say, what are you doing showing New York City? Well, this is to give you a perspective on these grid scales that we're representing. There's Manhattan, and here's the 10th degree by 10th degree box that we're looking at representing in these in the 10th degree, the CM2.6 ocean. So you're panning out, and you're starting to see the sea surface temperature sampled on a daily time, and you have a clock moving down here, and you're starting to see the representation here of the Gulf Stream. coming up around through the Florida Straits and separating off near Cape Hatteras, and providing a nice example of the mixing that goes on with the Gulf Stream. This, in fact, is not a jet-like enough. And part of the problem with the Gulf Stream in this model is that it becomes turbulent too soon. The jet feature should extend out a little bit further before it starts to break up. But nonetheless, that's what we get. We also have some Gulf of Mexico rings. Here's one of the rings now going off. And you see currents coming down from the Labrador Sea. And now we're moving to the tropics, where we have tropical instability waves, which are really beautiful to watch. Galapagos Islands, there's a really nice little cold piece of water that gets that originates from there. It's an impressive example of how a little piece of the planet can impact, a reasonably large area of ocean. And you can see the higher you go in latitude space, the smaller these features get. That's the Rossby radius effect due to the Coriolis force, getting stronger as you move away from the equatorial region. So now where are we going? We're going to the North Pacific, seeing the Kuroshio region. And one of the things that you might sort of notice is you see some flickering effect. That's because this is a coupled model, and there's synoptic waves in the atmosphere, storms that are moving. And if you look at it in real close detail, you can even see some of the tropical cyclones sucking up cold water as it moves through the ocean. I don't know if I can point one out to you from this movie here, but when you look at other simulation animations, you can see that feature of it. So you see a lot of this sort of stuff, and you go, is that a problem with the model? Is it a problem with the animation? No, it's because these storms are beating on the system. Now we're moving around South Africa and seeing the Agulhas region. This is a huge conveyor of water moving from the Indian Ocean that brings warm and salty water from the Indian Ocean into the South Atlantic. And you have this beautiful ring formations. And one of the problems with the models that are coarser than, say, a 10 kilometer is that these rings, these Agulhas eddies, tend to remain too coherent and stay, and they even transport almost all the way across the South Atlantic. Whereas in the real world and in these higher resolution, the 10th degree kind of models, they start to break up and become really turbulent and mix out before they get to the South Atlantic. And now we're moving into the equatorial Atlantic, seeing the Brazil current coming up here and breaking off some nice features and moving into the Caribbean Ocean, or the Caribbean Sea. So I really like this image. There's a cyclone moving across here, coming off of Africa. So I think it's a really neat pedagogical tool. It's on your system. If you want to show it in any of your classes, feel free. Let's now go back to the talk. So back to the coupled model, the three coupled models. Let's put our climate modeler hat on and say, what's the global mean surface temperature of the ocean look like as a time series over this 140 years? What's the global mean ocean surface heat flux, the heat going into the ocean itself? What's the global mean volume temperature? And what's the global mean steric sea level, all relative to the beginning of the simulation? Well, lo and behold, the blue is the 10th degree model, the highest resolution ocean. The sea surface temperature remains pretty stable. Whereas in the other models, they cool, and then the quarter degree model, after about 60 years, starts to warm again. If you look at the global heat going into the top of the ocean as a flux integrated over the area of the ocean, you get more heat going into the quarter degree ocean than you do into the 10th degree or the 1 degree ocean. Because you have more heat going into the quarter degree ocean, the global mean temperature of the ocean rises faster, and the steric sea level likewise rises faster than the other two models. So this is pretty important to understand now why these models differ. The global mean of the CM2.6 is about 1 watt per meter squared going into the top of the ocean, whereas the CM2.5, the quarter degree, is about 1.6 watt per meter squared. So 1 watt per meter squared is not a lot of energy. If you're trying to dry your hair with 1 watt per meter squared, it'll take you a few years to do that. But that's about the signal we're talking about, 0.5 watt per meter squared, 1 watt per meter squared, we're talking about with climate change. So if your climate model is simulating the climate system with a 1.5 watt per meter squared offset or imbalance, the ocean is absorbing too much of that heat. The system is going to start to warm up more than what you think of present day is going through. Whereas the 1 watt per meter squared with a stable sea surface temperature is a pretty darn good simulation. In fact, when we got this simulation, we had never seen a simulation this good at GFDL. Usually the temperatures, the sea surface temperature would be off. It would drift more like the 1 degree model here, where it would drift cold or drift too warm or what have you. So why is the 10th degree doing so well? Let's do another diagnostic where you horizontally average the temperature in the ocean and show it as a function of depth and time. The 1 degree, the 1/4 degree, and the 10th degree. So the thing to note is the drift in the ocean. There's more heat going into the ocean in the 1 degree and the 1/4 degree than in the 10th degree. Okay, and the 1 degree a little bit less than the 1/4 degree. The 1/4 degree has the most heat going in. So one thing I didn't tell you is that when you're running a 1990 climate simulation, you expect heat to go into the ocean. We just don't know how much, because the ocean has started out, the system's not equilibrated. Okay, so the ocean, the real ocean, is not equilibrated either. It's been undergoing forcing for the last few millennia that are still being transported through the system. So when you're running these present-day simulations, you're doing sort of what's called a committed warming experiment, where you're starting the ocean from levitus, or present day, which is really based on equilibrating for over thousands of years, and put it under an atmosphere with radiative forcing based on today. So the system is going to gain heat. The question again is how much heat, and so we can see that the drift in the 10th degree is much, much less than the other two models. And for a climate prediction problem, if you could run this for a prediction experiment, if you could run ensembles of this is a much better model to use, because you don't have as much climate drift to deal with. So we can break that down by basin and see similar features. The Atlantic in the 1 degree is really drifting a lot. So there's a lot of compensating errors in the 1 degree that you don't see when you do global mean. Whereas the 10th degree, for all the basins, typically has much less drift. And one thing to notice about this pattern is you see warming in the intermediate depths, but you have cooling in the upper 100 meters or so. So what that means is you're pumping heat. Again, the heat going into the ocean is positive. There's a positive amount of heat going in. And so what we're seeing here is that transfer, once it gets in the ocean, it's moving quickly through the upper ocean and then accumulating in the intermediate depths in all the models, but more so in the 1/4 degree than in the 10th degree. So it's a vertical heat transport question that I'm sort of leading you into thinking about. All the same. It's a 50-kilometer atmosphere, yes. So the horizontal patterns of bias, which are based on measuring the ocean simulation and comparing to observations, sea surface temperature and 730-meter temperature. You see generally cooling of the gyres in the 1 degree and the 1/4 degree, and less cooling here in the 10th degree. The biases that you see now, there's a lot of different physical processes going on here that contribute. The eastern boundary biases, the North Atlantic bias, the Labrador Sea bias, the Southern Ocean bias. So it would be more than one talk just to go through each of these patterns. The main thing I want you to take home is that there tends to be, in these two models in particular, generally cooling over warming. This is, back on that horizontal mean picture that I showed you before. There's an accumulation of heat in the lower resolution models, below the gyres in particular, the subtropical gyres. The 10th degree has a lot less of that accumulation. It has some problems in the North Atlantic, which I alluded to earlier, and I'm not going to talk too much about. But the sort of cartoon here that I want to leave you with is this typical warming under cooling, and the warming in the intermediate depths and cooling above. So again, there's heat pumping through the upper ocean that's accumulating in the intermediate depths. Less of that happening in the 10th degree model. So again, just to step back and summarize a bit, we expect the volume integrated ocean to warm since the 1990 radiative forcing provides a committed warming experiment. We just don't know how much a priori to expect that warming to happen. What's the rate at that warming? Drift is generally associated with vertical transfer of heat from the ocean surface into the interior. The differences in the drift correspond to differences in the efficiency of vertical heat transport in these simulations. The CM2.6, the highest resolution ocean, retains a stable sea surface temperature and roughly a watt per meter squared heat flux globally averaged over the ocean surface. This is actually consistent with the best that we can observe based on looking at radiative energy balances of the planet. So that's to get a stable sea surface temperature and a good top of the atmosphere heat imbalance is not an easy feat in itself. So what's the basic reason for the enhanced simulation, the higher climate integrity of the CM2.6? So to do that, we're looking at decomposing the heat budget. Fairly standard method, looking at the advection of tracer. Theta is your temperature field, and the U and the W are your horizontal advection transport and the vertical advection transport. And doing an eddy mean flow decomposition where the mean is some time mean. We're going to use 20 years. And the eddy is 20 years of monthlies, so a 20-year monthly climatology, so we can remove the seasonal cycle. So the seasonal cycle is not part of the eddy, it's part of the mean. And so what's left over in the eddy is predominantly these mesoscale eddy features, the transient eddy features, as well, of course, as other transient features such as tropical instability waves or interannual variability, features that you just can't take everything out and leave just the mesoscale when you're running a realistic model. But for most of what we're talking about, the interpretation of eddy is mesoscale eddy. And we do this decomposition, reasonably accurately. Everything is done online using online operations. So there's very little question about what is the numerical integrity of this. So we have the mean, and we infer the eddy based on knowing the left-hand side and deducing the mean piece, and then taking the difference to give you the eddy term. So U prime theta prime and W prime theta prime. And we're looking only at the convergence of these fluxes. So we don't have to worry about the fluxes themselves, which leads to lots of questions about rotational and divergent pieces of the fluxes. We're looking at just the convergence, the contribution of these fluxes on the budget of heat itself. So let's look at the budget of temperature, vertically integrated. The vertical integration of the time tendency of temperature over a 20-year period gives you this picture, the 1 degree, quarter degree, the 10th degree. The convergence of all the fluxes gives you this picture here, and the time average of the surface heat going into the top of the ocean. So the scales here are much different. This goes from -8 to 8, whereas this goes from -200 to 200 watts per meter squared. So if you were just concerned about the time average system, you would just call that 0, and say that you have the convergence of heat, or actually the divergence of heat fluxes in the ocean balancing the surface fluxes going into the top of the ocean. That's a very standard sort of balance that you get in the time mean. But we're interested in the transient here, so we're going to decompose this even further. But before we do that, I'd like to look at what's called Poleward heat transport. So we can once we have the vertical integral, then we can do a zonal integral and see what is going on insofar as transport of heat in the north-south direction in the ocean, and compare that to the best of our observational inferences that we have from INSEP and ECMWF, which are using inferential methods and a direct method from Ganeshaw and Wunsch. So the global ocean poleward heat transport in the 3 models, the black, the blue, and the red, and all these other data sets. We don't get as much export from the tropics as the data seems to indicate, at least the reanalysis-based methods, although we do pretty well from this in situ observations based on Ganeshaw and Wunsch in the southern hemisphere. The North Atlantic, in particular the Atlantic, we do very, very poorly for most cases. The Atlantic poleward heat transport is too weak, and I think that again is related to the poor representation of the overflows overturning circulation, the meridional overturning circulation in these models is typically not very good. It's nice to look at this bump here, though, in the North Atlantic, and that's due to an enhanced gyre transport in the higher resolution models, the quarter degree and the 10th degree. That feature is well captured by the high resolution models, and it agrees much better to the direct measurement from Wunsch, Ganesha and Wunsch, than the reanalysis products, which tend to be anemic in that part of the Atlantic. So that again is a whole story in and of itself. I of course believe the model and the Ganesha and Wunsch results more than I do the reanalysis results. Reanalysis is not really that easy to do in the Atlantic, so I think in particular the North Atlantic, it's probably not a bad thing to. I'm not being overly glazy-eyed with looking at the model there.
But the analysis is mounted like this as a residual, right?
Yeah, it's.
So you don't really know surface fluxes.
That's right. Yeah, there's lots of caveats with any reanalysis. But having said that, it's clear that we're not getting enough forward heat transport, especially in the lower latitudes, in any of these models. The Pacific, likewise, we're not getting enough export out of the tropics. The thing that I want to highlight here, though, is the rough agreement, at least between the quarter degree and the 10th degree, to within 5 or 10%. The agreement is pretty close, and in particular, look at the global here. Even all three of the models, except for this North Atlantic piece, the gyre, they're not that different. And for the most part, these polar heat transport figures seem to be driven by the same atmosphere. The same atmosphere is driving the three models, and so there's some balance that has to be met. If you have the same model, the ocean is going to try its best to meet that challenge given by the atmosphere. Within some caveats, in the North Atlantic, in particular, in the 1 degree, seems to not get that gyre circulation to the degree that it could, that it does in the higher resolution model. So the time is running out. Let me jump over now. We have been talking about lateral heat transport, but the real crux of the story for understanding the differences between the simulations and the heat going into the ocean is vertical heat transport. So let's, instead of integrating vertically as we did just now, let's integrate horizontally and throw away all of the terms that contribute to lateral transport, because we have no flux side boundary conditions, or we have a periodicity in the Southern Ocean. So all that's left in the time tendency of vertical heat, of heat horizontally averaged in the ocean, is vertical transport due to vertical advection and vertical subgrid scale processes, as well as the surface flux coming at the top of the ocean. So we're boiling everything down into a 1D vertical heat budget. So what you see is a bunch of fountain diagrams, or diagrams that look like there are fountains of stuff coming up. We have a 1 degree, a quarter degree, and the 10th degree, and a blow up of a particular piece of those three simulations. So we go from upper 200 meters here, sort of blowing up because there's a lot more heat going in that part of the ocean, and then 200 to 1600 meters, and we cut off the bottom of the ocean because it's just very quiet down there relative to what's going on here. We have minus 0.12 watt per meter squared, or no, degrees centigrade per year is the units here, and 0.12 degrees centigrade per year in all three of these figures. If you have a negative number here, that means cooling is happening locally at that depth in the ocean. If you have a positive number here, you have warming. And we have lots of different lines here due to lots of different physical processes going on in the simulation. We have the net tendency, which is the left-hand side here, which is this gray line, which is reasonably close to zero, but there is some drift, and it's in fact this drift that I'm most interested in, understanding why there's differences in that warming drift. This is a blow-up of the horizontal average tendency, and you see the positive values here of a warming drift over the upper 200 to 1600 meters. And so we have all the budget terms saved, and so we can ask the question, what is it that's creating that warming relative between the three models? So we have a parameterization of submesoscale processes. We have a parameterization of boundary layer processes. It's a non-local term that's called the KPP parameterization. We have vertical diffusion. We have advection. Plus, in this model, we have an eddy parameterization, and we have advection of the mean, and then we have the advection of parameterization plus the eddy. So there's a lot to talk about here. I want to just focus on the contribution of advection. And there's a mean component and there's an eddy component. And let's look at the 10th degree here. The advection from the eddies is tending to cool the intermediate depth ocean, whereas the advection of the mean is tending to warm the intermediate depth ocean. In all three of these simulations, when you go to the intermediate depths. When you go in the upper ocean, it gets a lot more complicated. In fact, in the upper ocean, the advection of the mean is cooling the ocean, and then it transitions down into the deeper ocean where it's warming. And so back to our thinking, where remember we had that cooling over warming. So the advection is locally cooling. It's moving heat from the upper ocean into the interior of the ocean, and that's what's going on here. You get the mean advection is cooling here, but then it gets to be warming here. Whereas the eddy piece is in the deeper ocean cooling, and upper ocean it transitions to a warming. So we can ask, we have all the information we want. We can ask in particular the difference between the 10th degree and the quarter degree. What is it? Well, you can see right away that the mean contribution, the warming due to the mean, is within some, 20% or so, roughly the same between the quarter degree and the 10th degree. It's this eddy piece that turns over in the quarter degree. It doesn't get as much, contribute as much cooling as it does in the 10th degree. So that's the clue right there that indicates the impact of the eddies in the 10th degree is much bigger than the impact of the eddies in the quarter degree. And of course it makes sense. The 10th degree is representing the eddies much more vigorously than it does in the quarter degree. And this is how it manifests in the heat budget.
It's like deep water kind of done more efficiently and higher. What's cooling?
Another way to think about this is you have mean flow pumping heat into the ocean and eddies pumping heat out of the ocean. If this was an isopycnal model, there would be no transfer. It would be an adiabatic interior. As you can see, there's almost a balance between the mean and the eddy piece here. If you sum these two together, I think mean plus eddy is the black line. It's pretty small until you get to the upper ocean here. So for the ocean beneath that line there, it's almost perfectly balancing. So part of it is a perspective that we're taking, which is based on z coordinates. So when you have your perspective based on z coordinates, you're going to have mean flow crossing geopotentials in one direction and eddy flow crossing geopotentials in the other direction. So if we then, this is going back to stuff that Christopher Wolf did, and others have done, instead of looking at a budget, if we instead start from the bottom of the ocean and vertically integrate these terms upward, we'll get a transport, which is totally analogous to meridional heat transport that I've already showed you, but instead look at vertical heat transport. So again, focusing on the red and the green lines, the negative now is a heat flux downward into the ocean, and the blue is a heat flux up out of the ocean. And focusing on these two figures here, the quarter degree and the 10th degree, you can see that the advection of the mean is pumping heat downwards into the ocean. I've already said this, but this is another representation of that. And the quarter degree and the 10th degree is marginally the same. In fact, there's a little more heat going into the upper ocean in the 10th degree, whereas the eddy piece is bigger here. And if you look at a particular depth, say at around 200 meters, you have about 2 petawatts of heat pumped up by the eddy component in the 10th degree model, whereas you have about less than 1.5 petawatts pumped up by the eddies in the quarter degree model. So that's a big difference. That's 30% or so difference between the two simulations, whereas again, when I was showing you the meridional heat transport, the meridional heat transport was very similar. So the representation of the vertical transport, I'm trying to convince you, is very different between these three simulations. And I don't have time to really go through all the details of the eddy parameterization in the 1 degree, so I'm focusing on the quarter degree and the 10th degree. So cartoons, this is kind of the take home of what's going on here. So there's many different ways of understanding baroclinic instability and what baroclinic eddies do. Let's take mid-latitude gyre, where temperature and density are roughly the same. You typically have these eddies that take in the available potential energy. Here's an eddy, and you're trying to relax that front into a horizontally homogeneous sort of picture here. In the process of doing that, the eddies are pumping heat upward, and that's sort of schematically illustrated here in this figure taken where you have warm water over cold water, and you have the eddy heat flux pumping vertically upward as well as horizontally. So if you integrate this horizontally, you'll get a vertical heat flux upward by that eddy piece. There's another component of the eddy heat transport that's really important in the high latitudes, especially in the Southern Ocean, and that's the along isopycnal diffusion nature of these heat fluxes. So now we are assuming the temperature isolines and the density isolines have some disagreement. And in the Southern Ocean, you have the temperature isolines more steeply sloped than the density isolines. So you have light water over heavy water, and you have warm water to the equatorward side of cold water. Again, this is poleward in the Southern Ocean. So the eddies are fluxing heat typically along isopycnals, fluxing tracers along isopycnals. So in this part of the world ocean, that flux of heat moves warm water up vertically and poleward. So it is a poleward and vertically upward transfer of heat by those eddies. So again, those are two different sort of cartoon schematics of why you expect these eddies to flux heat upward. And that's, again, what's going on in the simulations when you do these big budgets and globally average stuff. So general comments coming to the end. Are eddy parameterizations accurate enough for decadal prediction? I think that it's important to acknowledge here what we're finding here, that eddies are acting as a gatekeeper for pumping heat into the ocean interior. Getting the uptake efficiency properly represented in eddy and models or parameterized in coarse models is partly a key to accurately simulating the historical climate, including sea level, and making the predictions, decadal predictions. It may be less important, however, for transient climate sensitivity if one can assume the drift can be removed by subtracting the control from the scenario. So that's another talk about looking at transient climate sensitivity. And we did these studies looking at the transient climate sensitivity in these models and saw that other features of the simulations were more important than the details of the eddies. But I think that's still, I'm not quite convinced that that question's been fully answered. This is a reminder. The mesoscale, this is going back to the beginning of the talk. The mesoscale is really just a piece of the ocean's spectrum. This is from a paper by Dickey. I think it was a ecosystems paper, looking at the physical processes in the ocean as a time and spatial scale sort of spectrum here, going all the way down to molecular processes at the millimeter in the second scale, moving up to the climate variability processes. The mesoscale phenomena sort of sits in this oval here. Okay? Moving down in space and time, there's a lot of processes going on that we're still not representing, and some of which we're not parameterizing. Like Langmuir turbulence is a big area right now that people are looking at that has some impact on turbulence in the upper ocean that may need to be parameterized or represented. And so lots of these different scales are important. The mesoscale has been kind of a holy grail for the last 20 years because it is such a big piece of the ocean's energy field. The spectrum of the ocean has a big piece in the mesoscale. But we're starting to move into the submesoscale as well, at least in some of the process studies. And that's an important scale to start thinking about, especially for biology, because the submesoscale has really strong vertical transport associated with it. So I did a back-of-the-envelope calculation that, say you have, you want to represent everything completely, and if you want to direct numerical simulation of climate, which is like 10 to the, take a second time step, 3 times 10 to the 10 time steps over 1 second, 1,000 years, you would need about 10 to the 23rd discrete grid cells, 10 to the 27 discrete grid cells, which is 10 to the 4th bigger than Avogadro's number. So I think that's pretty unrealistic to expect we'll do direct numerical simulations of the ocean anytime soon, unless DNA or quantum computing can take us over that spectrum faster than anybody anticipates. So that's it. Thank you very much for your time. Yeah.
The latent heat flux is a pretty big contributor to the zonally average net surface heat flux. So do you have any feel for how important these mesoscale features are to the latent heat flux at the surface?
Yeah, I don't have any direct experience. I have a postdoc that did some work looking at satellites, and correlating satellites to fluxes going into the ocean, in the Southern Ocean in particular. And with the Aviso product, you can diagnose 200,000 or 300,000 eddy type events, and then you can correlate that to the fluxes going into the ocean. The answer to your question is, I believe that these eddies are very critical for air-sea interactions at that scale, and I think it's sort of a cutting-edge question. How the atmosphere feels the ocean. Do you need to have a one-to-one scale match? Do you need to have your atmosphere down to the same resolution as the ocean? And I think most people are starting to think that you do need, for the atmosphere to feel these fronts, like the Gulf Stream eddies and so forth, you need to have a representation of the atmosphere that's at the scale or close to that scale of the ocean fronts. Otherwise, you'll miss a lot of those dynamics that happen. So the turbulent fluxes are really, really felt in the atmosphere by these ocean anomalies that are moving quite fine scale. Whereas in the old days, people say, oh, the atmosphere is big, the ocean has these fine features, what do you care? But I think a lot of the satellite oceanographers are making a strong case that no, you do care. Yeah.
It's just, I'm kind of struck by your emphasis on the subsurface, 200 meter intensity flux. So I'm curious, if you will make a movie of eddies, say 300 meter, whatever, you probably see very different from what you see at the surface, because the two are not actually the same.
Yeah, the eddy features in the Southern Ocean reach down pretty deep, because the Southern Ocean has.
All the other parts is from.
You're right, though.
The eddies, the typical surface, they are very different.
They have a baroclinic mode sort of structure, and when you have a thermocline, that baroclinic mode structure is largely enhanced in the upper 500 meters or so. You're right. But it does reach down to the depth of the bottom of the gyres, 700 or 800 meters, maybe 1,000 meters in some parts of the ocean. But deeper outside the Southern Ocean, you're right, the eddies are not that big a deal. But part of the drift, the biggest part of the drift that I was talking about was in the upper, above 1,000 meters or 1,500 meters or so. So I agree. The deep ocean, the eddies, I wouldn't discount them all the way in the deep ocean, but they are much less amplified down there.
Yeah, there are two very general questions. One is about, if we cannot afford the global resolution, what about some regional resolutions in any regions such as the Gulf Stream or Croatia Station, etc.?
So regional question?
I mean, for regional resolutions.
Yeah. Yeah.
Some areas can use very extremely high resolution without mesoscale radius, or even closer by high resolution.
Exactly. So maybe I'll ask a question based on, or I'll answer based on what I think is your question. Is there a role for regional enhancement in looking at climate questions? And I think the answer is yes. But I had a nice discussion with a couple of y'all earlier today, a couple of your faculty, and it's hard to do. The boundaries are a real big question. And if you're interested in global climate questions and sensitivity of the climate system, what you do at the boundaries of these regional models can be a really, really big deal. If you're interested in regional questions like impacts along the east coast of the US, then you might nest a high-resolution regional model inside of a global model and look at some of the one-way interactions. But there's also, there's an interaction from the large to the small, but there's also an interaction from the large to the small, to the small to the large, that you would potentially be missing if you had just that one-way interaction. So one of the best ideas, I think, for doing that is to have a global model with regional enhancements. So the regional enhancements are felt by the large scale, and the large scale affects the small scale. Even that, I think it was Edmund Chang we were talking, say you resolve a tornado over Oklahoma. You have a multi-nested atmospheric model. Well, there could be some impact from that tornado on the larger scale that you're missing because you're only representing the small scales in a region that's just very small. So there's always that question. And so we've typically focused at GFDL, at least for climate, on models that have the same resolution or quasi-uniform around the globe. Which we sacrifice the being able to do those questions like you're saying, but that's sort of the choice.
That's great. That may come to my second question. What would be the main issues about the eddy mesoscale eddy parameterization in coarse resolution? Can we solve that issue and not use a high resolution?
So the eddy parameterization question I hinted at is really been a problem that's been around now for 30 years or so, and there's some very good ideas out there that have been thrown around, and all the 1 degree class models have a representation or a parameterization of eddies. The schematics I showed at the end here are largely the slumping of the isopycnals and the diffusion of tracers along isopycnals. Those are based on ideas. Those are parameters. Those processes are parameterized reasonably well in the models. The questions now are, what is the diffusivity that you use if you believe the closure is a diffusive type closure? Does it have a vertical structure? How does it depend on the flow field itself? Is there some stochastic element to the closure that you might have that you're not representing if you just have a diffusion operator in the model? And so there's lots of variance on those parameterizations that I showed you, sort of their schematics from, that are still being thrown around the community today.
Probably have to break for lunch, so if you still have questions, just
Yeah, just quick, you don't really have to go to the macro scale, right? I hope you will.
I'm throwing that out as a cartoon, but
Yeah, it's enough to go to inertial subrange, because then you can parameterize SJS precisely, just using similarity theory. So what's your inertial subrange scale in the ocean?
I have never seen anybody make that statement before. That's an interesting comment. What is? Yeah, in the ocean, I'm not sure because we don't know how the ocean dissipates its energy. Is it bottom drag? Is it internal waves? Is it lee waves? Is it boundary layers?
You cannot resolve everything perfectly, but what is good enough? That's my kind of.
Yeah, until we have a simulation that tells me what is good enough, it's hard to answer that question.
On the order of a centimeter.
Yeah.
No, that's not true.
Yeah.
It's one man.
Yeah.
But it should be some reasonable scale. Like in atmosphere, for example, I would claim it's like 10 meters. That's enough because it's in any regime it's basically an inertial subrange.
Yeah.
And everything else which nature does is basically just cascading.
So the direct cascade, not the inverse. So you start to get to the edge of the direct cascade.
Right.
Yeah.
So in
Yeah.
atmosphere, I would say it's maybe the inertial subrange which is measured is something like several hundred meters.
Yeah.
So to resolve it properly, you need like several tens.
Yeah. Yeah.
But that's it. So as long as you go to that, I would claim that any more increase in resolution won't apply.
That's a good point. One point of contact I have with that is that there's some nice study looking at the question of when you need to have a non-hydrostatic in the ocean. So the traditional argument is once you get to a kilometer or finer, you need to go non-hydrostatic. This guy was saying that you can have it in the ocean. Hydrostatic is pretty good for like doing convection problems down to like 100 meters or so. So if that's of any indication that maybe the inertial range is a little smaller in the ocean than it is in the atmosphere, I kind of think it might be.
Several meters.
Yeah, yeah. That's totally a guess though, based on some.
It's better than 10 to the minus.
Fair enough. So you can reduce that from, you can maybe go to 10 to the 20th. I don't know.
Then you can go much less than what
Yeah. I'll modify that for the next talk I give because there'll be somebody in the audience as smart as you that will ask that question.
About 10 times.
There's another, there's a Reynolds number argument that you'll see, the resolution should go as the Reynolds number to the 4/3 or something like that. And, the Reynolds number in the ocean is, 10 to the 6th, 10 to the 7th, depending on the scales.
Just in atmospheric actually simulation has been shown when you reach certain scale, and then you keep increasing resolution.
Doesn't do much.
Solution
Okay.
doesn't change.
Yeah. Good point. Fair point. Yeah. Thank you.
Now we can break off. Also, set aside